Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be really culminating our work with logarithms and exponents to take all of this information that we've been learning about, in particular, the properties of logarithms and exponents, to go ahead and actually solve both logarithmic and exponential equations. And then we're going to talk about the equivalence of exponential and logarithmic expressions as a way of helping us to solve these equations. What I'd first like us to do is examine a logarithmic equation. You can see that a logarithmic equation is one where logarithmic expressions are part of the equation. And we need to solve this for x. Remember, anytime you're solving an equation, you're solving for an unknown variable or variables. So in this case, we need to figure out what is x that makes both sides of the equation the same quantity. Well, there's a couple steps that we should do when attempting to solve this. The first thing that we're going to need to do is to make sure that all logarithms are of the same base value. So in all of the logarithms that you're working with here, make sure they have the same base value. That's going to be very important. So here, in both logarithms, they have a base of 5. So we're good. We can go ahead and start solving this. The first thing that we should do here is really, if I have multiple logarithms, that's not really that fun to work with, is it? Right? Having multiple logarithms on each side of the equation. Wouldn't it be better if I just had one logarithmic expression? Like when we would work with fractions, we'd sometimes say, oh my gosh, working with these fractions and these rational expressions, gosh, they were kind of annoying to deal with. Wouldn't it be better if we just had one of them to work with as opposed to multiple? Same thing that we saw when we had square roots in other radicals, in radical equations. We said, wouldn't it be better if we just had one to work with instead of multiple? So I'd like you to take a minute and try to think to yourself, is there any way that we could turn this equation into something where instead of having two logarithms, we only have one? Well, hopefully you're thinking to yourself about the properties of logarithmic expressions that we went over in a previous talk. What we want to do here is isolate the logarithmic expressions. What we're going to do is we're going to get these by themselves, meaning get them to one side. So I'm going to add this log base 5 of x plus 4 to both sides. Log 5 of x plus 4. And we're going to end up with log 5 of x plus log base 5 of x plus 4 equaling 1. How does this help us? Well, wait a minute. We know what to do when we add logarithms together, don't we? We can condense this expression down. If you're adding logarithms, and again, they have to be of the same base. If these bases were different, these properties wouldn't work. So if we were adding logarithms together, we could have said that that's really just multiplying the arguments together. When you were taking the logarithmic expression, this was the product property, and you were multiplying two arguments together, you could separate that with addition. And you could go in the reverse. If you're adding two logarithms together of the same base, you can multiply their arguments together. So let's go ahead and multiply the x and the x plus 4. We should end up with a quadratic here, and we'll end up with x times x is x squared, and x times 4 is 4x, and that's equal to 1. Okay, so we've isolated the logarithmic expression, and I'm going to say condense the logs into one expression. meaning get the logarithmic expressions to one side and condense it down into one expression. We were saying, okay, this is probably better than having multiple logarithms all around to account for. We can use our properties to combine them all into one expression to deal with. Now that we have a single logarithm equal to a specific number, I want you to pause the video again and take a minute to try to think to yourselves, how can we solve for x? Right away, I can't work with this x. Some people think, well, what if you subtract 4x from both sides? Can you do that? No, you can't do that. Because x here, the 4x and the x squared, they're trapped in the logarithm. We need to get them out of the logarithm. But how can we do that? Again, pause the video, take a minute, and see what you can come up with. Hopefully this wasn't too difficult of a task for you, because this looks a lot similar to something we started with way back in the beginning sections of working with logarithms, when we would have something like log 5 of x equaling 1. And we say to ourselves, how do we figure out what x is? Well, we know that the logarithm could be rewritten as the exponential 5 to the first power equals the argument x. And we knew what x was, that was just 5. So by having a logarithmic expression, we can rewrite that into an exponential. So let's go ahead and do that here. I'm going to take the base 5. Its exponent is the 1 here. Let me clear that. And what it equals is the argument, x squared plus 4x. Once we've isolated the log and condensed the logarithmic expressions into a single expression, we can now rewrite this. We can rewrite the log equation as an exponential equation. I'm going to abbreviate that exp and then equation eq. So here we have 5 is equal to x squared plus 4x. Well, what do you notice about this problem? This is a quadratic equation. We've gotten rid of the logarithms and we're ended up with a quadratic equation. What we can do is we can say this is 0 equaling x squared plus 4x minus 5. And now we need to solve this. We have all different types of methods for solving quadratics. Remember, we have the quadratic formula, we could complete the square, or we could attempt to do the zero product property. I'm looking at this and I'm thinking this is pretty easy to factor. Why don't we try the zero product property? So I'm going to factor this polynomial down to x plus 5 and x minus 1. Those will multiply to give me negative 5, but add to give me 4. So if I set each of these equaling to 0, let me write that a little nicer here. I set each of these equaling to 0, I would get x equals negative 5 and x equals positive 1 as my solutions. So let's go ahead and write down the last step here, rewrite the logarithm as an exponential equation, and then solve the resulting equation. Now, in this case, we ended up with a quadratic equation. That doesn't always happen. You might have ended up with a linear equation to solve, okay? But here we ended up with a quadratic. Now, what do you think about these answers, negative 5 and 1? What do you think about them? Think back to the work that we did when we were solving rational equations and radical equations. Do you remember working with, what did we call those? Extraneous solutions. Well, remember, extraneous solutions occurred when you had an initial equation that had a restricted domain and you turned it into an equation that had an unrestricted domain. Remember, logarithms have restricted domains. They don't continue on for negative infinity to infinity. Their graphs have these curves with asymptotes, right? Whether it's growth or whether it's decay. Remember, we had a whole section on finding the domain of logarithmic functions. So we have an equation here that has a restricted domain. These expressions can't have certain values plugged into them, but we turned it into a quadratic equation where you could plug anything you want in. So it's very possible that these solutions right here to the quadratic are going to be extraneous solutions for the logarithmic. What we're going to have to do is check our answers. So I'm going to say for the last step, check for extraneous solutions. So when we check for extraneous, okay, whatever, close enough. When we check for extraneous solutions, we have to plug both of these values back into the logarithm. Well, one thing I'm noticing right away, what would happen if I plug in -5? So let's see if I have some room here. Log 5 of -5, does that equal 1 minus log 5 of -5 plus 4? What do you think? Is this going to be allowed? Hopefully you're saying right away, no, this isn't allowed, because we cannot have a negative value for the argument, right? Take a look here. Log of -5, that's not allowed. And then we have -5 plus 4, well, that's just going to be log of -1. Again, that's not allowed either. You can't have negative values for the logarithms. So right away, we're seeing that 5 is in fact an extraneous solution. Here, let me try to clear some space here. We know that 5 is not a true solution. We're going to say that it is extraneous. Now let's test 1, and let's see if 1 works. Log 5 of 1 equals 1 minus log 5 of 1 plus 4 is 5. Okay. Log 5 of 1. Well, we could put that into our calculator. We could do the change of base formula. We could do natural log of 1 divided by natural log of 5. We could do log base 10 of 1 divided by log base 10 of 5. But this should actually be pretty easy for us to figure out. 5 to what power gets us 1? That's just a 0. And then we have 1 minus log 5 of 5. 5 to what power gets us 5? That's a 1. And hey, what do you know? It works. So x plus 1 here is the true solution. Again, we have to test this to make sure that it's working. But we came across a solution where we had 1 extraneous and 1 actual solution. Okay? Always, always, always check your work. Now, sometimes both might in fact be a solution. Other times, really, it might just be one, or other times, maybe none of them will be solutions. It all depends on the initial equation and the setup to it. Now, with this procedure in mind, let's go ahead and try some practice problems out. What I'd like you to do is take some time to solve each of these equations. I want you to figure out what x is for all of them, and I want you to check your work to make sure that you have correct solutions and not extraneous. So pause the video, take a couple minutes to yourself, and let's see what you come up with. All right, well, hopefully you had some time to work through these problems and were able to come up with the correct solutions. You'll notice in the first problem here, we again have 2 logarithmic expressions, and they're on separate sides of the equation. So what I did was I decided to move them over to the same side. So I added the log 3 of x, and by adding logarithms, what I'm really doing is multiplying their arguments. So I multiplied the x and the x minus 8 together to get x squared minus 8x. So this is how I combined together the 2 logarithms into 1. And that's still equal to 2. So since I had one logarithmic expression on one side and that equals a number, I was able to rewrite this as an exponential. I took the base 3, the exponent 2, and the argument is what it equals. Now this was a quadratic equation. I had a 9 equals x squared minus 8x. So what I did was I rewrote this to be x squared minus 8x minus 9 equaling 0. I took the quadratic, set it equal to 0, and then I decided, well, I could do the quadratic formula, I could complete the square. Luckily in this case, I could actually factor the quadratic down, so I decided to use the zero product property. I factored it into x minus 9 and x plus 1, because negative 9 and positive 1 add to negative 8, but they multiply to negative 9. So my solutions were x equaling 9 and x equaling negative 1. Now hopefully you were able to get to that part, and then hopefully you also went and you checked your solutions. Now obviously negative 1 isn't going to work here, because negative 1, immediately if I plug it in right there, I know it's not going to work. Also, if I plug negative 1 in for here, I would get a negative 9. Again, you can't have a negative argument, so that wouldn't work. I then tested 9 out. When I plugged it in, I actually got a true solution. 9 and negative 8 made a 1. And then here, I just plugged 9 in, and I actually got it to be, I think it came to 0 equals 2 minus 2. So it actually turned out to be a true statement. So x equaling 9 was the correct solution. X equaling negative 1 was the extraneous. For the next problem, I also had two logarithmic expressions. Luckily, they were on the same side of the equation. This time I was subtracting. Remember, when you are subtracting logarithms, you're being asked to divide their arguments. So I went and I divided the two arguments. I got x plus 3 divided by x plus 2. Again, this is one whole logarithmic expression equaling a number. So I could just rewrite that into an exponential. I rewrote the base 2, exponent of 1, and then the argument is what that equals. So I had 2 equaling x plus 3 over x plus 2. Now I'll show you really quick in a different color kind of what I did here in case you're struggling to see. I just multiplied both sides by x plus 2. Okay, that cleared the fraction here, and I was left with a 2x and a 4 on this side, and x plus 3 on the other side. And when I solved that, I got x equaling negative 1. That did test out to be a true solution. So when you plug it in, you should actually get this to work out entirely. For the next problem, I saw that I had 3 logarithmic expressions. 1, 2, 3. So I decided, put them all on the same side. So I had a positive logarithm, and then I had 2 negatives. Again, remember your properties of logarithmic expressions. When we condense things down, those negatives meant put them in the denominator. So that's what I did. I put the 2 in the denominator and the m minus 3. Well, if both of them are in the denominator being multiplied together, I just got a 2m minus 6. And the 4m stays in the numerator. So again, we could go ahead and rewrite this. Keep in mind, there's no base that's written here. Since there's no base that's written, what we're implying is that this has a base of 10. There's like an imaginary 10 right there. Now, I should point out, this sometimes varies. If there's no base written, in this class, and in my videos, I always mean that you should assume it's an imaginary 10. Our textbook uses that, and in fact, that's how our calculators are actually programmed. Log with no base written just means there's an imaginary 10 right there. However, in other classes and other books, and actually in quite a lot of standard practice, if you had nothing written, if you had log of whatever with nothing written, they mean that should imply the natural logarithm. If there's nothing written, some books say, then you assume the base is e. Now, we don't do that in this class, mostly just because of how our calculators are programmed and how the book publisher uses the symbolism. So we're going to leave it as a 10 here, okay? So I just wanted to point that out just in case anyone was looking at a different textbook or a different series of problems online and they were intending for you to use an E here. But for us, we're sticking with 10. And really this problem doesn't matter because if we rewrote this as an exponential, we would have the base 10 or whatever base to the 0 power equal 4m over 2m minus 6. What's 10 or any base to the 0 power? 1. So that's how I got this expression right here. 1 is equal to 4m over 2m minus 6. Well, I just multiplied both sides by 2m minus 6 to get that to cancel out and to move it over to the other side. And then when I solve for this, I got m equals negative 3. Well, one thing that you should notice right away, can you plug negative 3 in here or here? No, because if you plug in negative 3, you get a negative 12 for the argument right here, or you would get a negative 6 for the argument here. So we should be saying to ourselves, obviously, this negative 3 is an extraneous solution. So hopefully these problems are making sense to us here. You can see in this case, we really don't have a solution for this equation. Well, you might argue negative 3 is a solution if you allowed for maybe complex valued logarithms. If you went into the complex plane, then your domain would be different and you'd allow for different quantities. But instead, we're going to just stick with the real solutions here, and we're going to say no, negative 3 is extraneous. So this, for the time being, has no solution. Now what I'd like to do is talk about a specific property, or really a technique that might help us out when solving logarithmic equations, especially when they fit this form. If you have a logarithmic expression equaling another logarithmic expression, and they have the same base, their arguments, we're going to say, are equal to each other. Let's read the statement. If x, y, and b are real numbers, remember this symbol just means they are real numbers. So any number on the number line, and all of them are positive. Don't deal with negatives, remember. So all of them are positive, and by the way, don't have the value b be a 1. Then we can say if the logarithms are equal to each other, then their arguments should be equal to each other. And that should make sense to us, right? If I had log base 5 of some number equals log base 5 of 2, well, aren't these really just the same thing? Because we're saying they're equal to each other. It's this, everything is the same here. The only thing missing is the argument, so obviously that should be a 2. And this expression, this equivalence of the logarithmic expression property really should be fairly obvious to us. And it's going to be very helpful when we try to solve a problem like the one we just worked on. I'd like to rework this problem using this expression property as our method for solving it. Notice that the one side has log of 4m, and we can say that's like log base 10. This side, let's go ahead and let's combine it together. We're adding the logarithms, so I'm going to multiply their arguments to get log of 2m minus 6. I just multiplied the 2 and the m minus 3. And you can say the log is 10. You could write it, or you could just leave it blank. Well, since the logarithms are the same, the bases are the same, and we're saying they're equal to each other, then we could say 4m equals 2m minus 6. That's what we had in our previous problem. we had that expression right here. But the thing is we did a little extra work to get to that. We went and we just moved everything over to the other side. And moving that over, we had to rewrite it as an exponential and simplify from there. What this property is saying, you don't have to do all that work. As long as you can get a logarithm equaling to a logarithm and they're the same base, you can set their arguments equal to each other. And you could solve from there, and it would still work out. Now, this does not always work. What I mean is, you can't use this for every problem that you come across. For example, I couldn't use it for this problem. Log base 3 of x minus 8 equaling 2 minus log base 3 of x. The property said you had to have a logarithm equaling a logarithm. But notice here, I got a 2 thrown in, right? I got a specific constant. So the property really wouldn't work for that. I'd have to manipulate this even more. So really, try to be careful when using it, okay? Really, it only works when you have an all logarithmic expression. You could try to use it in this situation, but you would have to rewrite 2 as a logarithm, and you would have to write like log base 3 of 9, right? That's what 2 is with log base 3. Then you would have to combine it together. You could do that, but does it really save you any time? I mean, this problem was fairly quick for us to get to here, so how much time does it really solve for you? You see what I'm saying? So, something to consider. Now let's go ahead and let's try talking about how to solve exponential equations. So our work with logarithms was really centered on our ability to isolate logarithms and use the properties to condense them down. We're going to have a little different method here for exponentials. Again, same thing as always. We want to figure out what x is. We have 2 to the x plus 3 power equaling 7 to the x power. We need to figure out what x is. When we had the logarithmic equations, we needed to figure out what x was, but we had to get it out of the logarithm, right? We weren't able to work with it inside that logarithm. We had to get it outside. Similarly, when trying to work with these x values, they're trapped in the exponents. How are we going to work with the x's when they're trapped in the exponents? Well, we have to get them out. What I want you to do is pause the video and take a couple minutes to think to yourself, okay, if I need to solve for these x values, how can I get the x values outside of the exponent and make them just like regular numbers? How can we go about doing that? Think back, what properties do we have? Think back to the work that we've done in the past with logarithms and exponents and think, what could I do to get those exponents out into the regular numbers? Well, hopefully you caught the trick. One thing that we can do, and really the main thing that we should do for getting the exponents out of the exponent and down into the regular numbers, is taking a logarithm of both sides. What I mean by that is this. Let's take log base 10 of 2 to the x plus 3. And let's take log base 10 of 7 to the x power. Am I allowed to do that? Well, of course. This equal sign means these are the same numbers. Whatever x is, you're going to get the same number on both sides. So if I take the logarithm of a number, that's going to be the same thing, right? Now, I can take the log of both sides, but it has to be the same base. So notice I use the base 10 here. Do I have to use base 10? No, actually, I could even use, just for practice sake, I'll use the natural log of both sides. That's of base e. Again, it doesn't matter, right? Pick whatever base you want. Use log base 15, whatever. It still works out. What we're going to do here is use our properties of logarithms. This was the only situation we had where we could take the exponent and move it out front. Remember that property that said if you're taking a log, I think it was if you're taking a logarithm of some quantity to an exponent, then you could bring that exponent out front and multiply it by the log of that quantity. So we're going to use that property right now. Let's go ahead and let's move the x plus 3 out front, and we're going to multiply that by the natural log of 2. And here, let's move the x out front and multiply that by the natural log of 7. Now, before we move on, let's go ahead and write down some of the steps that we've just done here. Step 1, take a log of both sides. So take a logarithm of both sides, and I'm going to say in parentheses here, make sure it is the same base value. So we got to make sure you're taking the log of the same base value. You don't want to mix that up. Once you have that, use the property to move the exponents down. By that, the property was, and I'll rewrite it here, let's see, it was the natural log of x to the p power equaling p times the natural log of x. So this is the property that's going to be central to us solving logarithmic equations. So we did that here. Notice that I wrote x plus 3 in parentheses because x plus 3 was the entire exponent. Okay, it wasn't just x, it wasn't just 3. It was all of x plus 3. So I need to take all of x plus 3 and multiply it to the natural log of 2. Well, let's see. We can go ahead and distribute the natural log through, and we get x times the natural log of 2 plus 3 times the natural log of 2 equals x times the natural log of 7, okay? Oh boy, this is still kind of weird. I want to get x by itself. I need to solve for x, but I'm taking x and a natural log of 2 and x and a natural log of 7. Well, this shouldn't be that difficult for us. This is similar to what if we had the equation 2x plus 6 equaling 7x, something like this. This logically would be the exact same situation. Well, not the exact same, but same kind of format. All that we have here is a number. Natural log of 2 is just a number. It's a decimal that goes on forever. It's not a nice whole number, but it's still a number times x. That's like this situation, a number times x. And then we also have a number, the natural log of 7, again, is just some number times x. Well, that's what we had right here, a number times x. Again, it's not a nice number, but it's still just that. So what did we do in this situation when we had nice whole numbers? Well, we would just go ahead and get all of them to combine together. So we'd isolate all the terms with x on one side and everything without x on the other side. Okay, I guess we could go ahead and do that. Let's see. I'm going to move the natural log of 2 times x to the other side. And I end up with 3 times the natural log of 2. Again, this is just a number. Type it in your calculator. It's a number. It's a decimal. And this is going to be equal to x times ln of 7 and minus, oh boy, I'm running out of space here. Let me try rewriting this. We had 3 ln of 2 equaling x ln of 7 minus x ln of 2. Okay, so we got the x terms on one side and everything without an x on the other side. But here's the trouble. How do I combine these like terms, right? Because these numbers aren't like nice whole numbers or even fractions or anything I can add together, right? They're irrational almost, like they go on forever and ever. Well, keep in mind, what did we do when we had stuff like radicals? Say I had 3 equaling x times root 7, times root 7 plus x times root 2. Well, we couldn't really combine these together in any way, like we couldn't add them together. So what did we do instead? We would factor out the x. We would factor it out and just have those values left to add together. So let's do the exact same thing right here. Let's factor the x out. So we have 3 times the natural logarithm of 2, okay? That's equal to x. I'm factoring that out from both of these, and we're left with the natural log of 7 and minus the natural log of 2. It's a little hard to read. Let me see if I can write that a little nicer. Natural log of 7 minus natural log of 2. And there we go. We've pulled the x out, so we have, again, some number times x. And that's equal to another number. I haven't written what the decimals are, so I'm just kind of leaving this as is. But again, just know this is going to be some number. Put it in your calculator. ln of 7 minus ln of 2. You'll figure out what that is. How do I get x by itself now? Well, keep in mind, I'm saying x times all of this. So, divide both sides by ln of 7 minus ln of 2. ln of 7 minus ln of 2. All that I'm doing here is isolating the x. We get x is equal to, on the bottom we have ln of 7 minus ln of 2, and on the top we have 3 times ln of 2. This is what x is equal to. So go ahead and actually type this in your calculator and see what you get. I'm going to take 3 times the natural logarithm of 2, and I'm going to divide that by, I'm going to try to put this in brackets, the natural log of 7 minus the natural log of 2. I'm getting x is approximately 1.659884267. Something like that. And sure enough, that's what my x is going to be. So what did we do here? We took the log of both sides, and we had it the same base. Then we used the property to pull the exponent out front. Step 3, really, it depends on where you go from here. It depends on what your equation is. Once you pull the exponent out front, I'm just going to say isolate all x terms. So get all the x terms together on one side. We then factored out the x. So we factored that out almost like a GCF here. And once that was factored out, we solved for x. We just divided actually both sides by that quantity. So this is a way we can go ahead and solve an exponential equation. You'll notice that I did this without actually figuring out what the natural log numbers were. I just left them almost symbolic representations of the natural logarithms. Now, I understand that this is sometimes difficult for students to really wrap their heads around. It's important to remember, and maybe you want to, as you go through this, highlight every time you have natural log of a number. Highlight that every time so you know that's just a number, right? What I will say is this. To help students out, it's sometimes easier when they're at this step to stop writing the natural log of 2 and the natural log of 7, etc., and actually start writing decimals. What I'm going to do right now is I want to resolve this equation for us. But this time, instead of using representations for the natural logarithm, or whatever logarithm we picked, what I want us to do is actually try to solve this using decimals. So I'm going to clear some space here. And I know what my solution should be. What I'm going to do is try to get that solution again, but this time without having to worry about the natural log representation, because sometimes students get tripped up in all of this work. So what we did here was we distributed the natural log of 2 to get x times ln of 2 plus 3 times ln of 2 equaling x times ln of 7. What we could do is actually figure out what these decimals are. So I'm going to type ln of 2 into my calculator, and I get a long decimal. What I'm going to do is I'm going to round it to, the more places you round, the better. So I'm going to try to go to 3 decimal places. And I hope I have enough room here. I'm going to get 0. Let me rewrite that a little nicer. 0.693. That's the natural logarithm of 2 times x. 0.693 times x. Plus, natural log of 2 times 3 is 2.079. Again, we're just rounding. And the natural log of 7 is 1.9459. So I'm going to round up to 1.946 times x. All that I did here was, instead of having a representation for what the decimals are, I actually wrote the decimals out. I didn't write all of the decimal, I just wrote the first 3 digits. The first 3 decimal places. So I'm in the thousandths place. So sometimes this is easier for students because they can obviously say, oh, well, let me just subtract this value from both sides, 0.693x. We're going to end up with a 2.079 equaling, let's see, 1.946 minus 0.693. That gets me a 1.253x. And I could divide this on both sides. And what will we end up with? 2.079 divided by 1.253, we get 1.659217,877 for x. Well, what do you notice about this solution here? Remember, when I solved the previous solution where I used the representation for ln of 7 and ln of 2, where I didn't round off, I had x was equal to 1.659884267. Here, we agree to those 3 decimal places, 1.659. Now, granted, we could say, well, you really want to round up there and round down here, but that's still fairly accurate. So rounding to the 3rd decimal place here didn't get us the closest approximation, but it was fairly good. The more decimals we round to, probably the better the approximation would be. If you wanted to get the best possible approximation, which would be this value, you would want to stick with just working with the natural logarithm functions and typing those into your calculator. If you're thinking, you know what, I'm going to mess up on that process, I'm really struggling to see how ln of 7 really represents a number and how I can get x by itself, go ahead and try working with the decimals here. This is fine with me. I have no problem with that, right? I have no problem with you actually looking to see what is that number. What I would like you to do, though, is I want you to round your answer, what you get for the logarithms, to at least 3 decimal places. I want us to be in the thousandths place. Don't round it to the tenths place. Don't round it to the hundredths. Try to go to the 3 decimal places. Or if you're up for the challenge, maybe you want to go to even more decimal places. Why not? You got a calculator. You can make it work. Just be careful with what you type in and make sure you're writing down accurate steps. What I'd like us to do right now is take a look at these practice problems and go ahead and try to solve them using this technique of working with logarithms on both sides. Now, I'm fine if you use either technique. Either you stick with the logarithmic representation, or if you convert it right away to decimals. I'm fine with either, your choice. For me, I'm going to stick with the logarithms, so when we get to the answer key, take a look to make sure that you have the correct solutions, okay? Okay, well, hopefully you were able to work through these problems in whatever way made sense to you. I went ahead and I stuck with the natural logarithm representations. Again, you didn't even have to use the natural logarithm. You could have used log base 10, you could have used log base whatever you wanted, okay? And of course you could have done this where you actually went and figured out what the decimal approximations of these quantities were. But I went ahead and I just stuck with the standard values of the natural logarithm representation, and we're going to see if we go ahead and get the exact same solutions. We probably should. So let's start by noticing that we took the natural logarithm of both sides. So when taking the logarithm of both sides, we got the exponents to come out front. There wasn't an exponent here, so I just left it as the natural log of 64. But with that, I was able to distribute the natural log of 4 through. So what I did, I tried to be a little clever here. Instead of saying 2x times the natural log of 4, I said 2 times the natural log of 4 times x. And I put that in parentheses to kind of show to us that that's just a number, okay? And then negative 1 times natural log of 4 is just negative natural log of 4. So what I did here was I added that over. So I had everything without the x on one side and everything with x on the other side. Then, to solve for x, I just divided by that 2 natural log 4. I divided that to both sides here. And we got this big long representation of the natural log of 64 plus the natural log of 4 divided by 2 times the natural log of 4. That actually just got us a solution that was a whole number, a 2. Now, you should also be able to get this if you use decimal approximations. If you rounded, you might still end up with a rounded decimal at the end, like 2.0000 maybe, or 2.0001, okay? That might happen if you go ahead and actually round off and don't use the symbolic representation either in your calculator or on the computer in some type of software system. Because when typing it into your calculator, yes, you're getting decimal values, but if you type everything in, it's really working, the calculator's working with the function itself, and it's doing a little manipulation. So the benefit of this, leaving things in symbolic form, is you get either a much more approximate solution, and you can get an exact solution if one exists. But it still should be fine. You'll be close enough if you use decimals. Now in the next problem, I went ahead and did the same thing. I had the natural log of both sides. And by taking the natural log of both sides, I moved the exponents out front. Here I moved the negative x plus 1, and here I moved the 5x out. I distributed the natural log of 16. And again, I tried to be fancy here. I wrote the natural log of 16 in parentheses times x, because we're so used to seeing numbers times x, like 5x, 3x, 2x. We don't usually write x5, x3, x2. So to make it a little easier for us, that's why I put the numeric values out front of the x. And again, got to get the x's on one side, so I moved everything that had an x to one side, factored the x out, and divided what was left over. So I got natural log of 16 divided by 5 times the natural log of 8 plus the natural log of 16, which approximates to 0.210526. Something about there, okay? If you rounded it to 3 decimal places, we should agree to about 3 decimal places as well. And again, you can see the same process right here. Natural log of both sides. Move the exponents out front. And with those exponents moved out front, I could go ahead and distribute. Isolate the x, factor it out, and then divide it over to both sides to get this representation. My answer is negative 4.240170,316. Again, you don't have to write all of these decimals out. I like us to round to 3 decimal places, but obviously the more you give numerically when we're trying to find exact solutions, the better we would have an approximation of. Now what I'd like us to do is, as we looked at working with logarithmic expressions, I'd like us to look at the exponential expressions and this special property about the equivalence of exponential expressions. In this situation, we're saying, say you're taking a base value b and raising it to a power. And if we say that's equal to base raised to another power, what can we say about those two exponents? So here, x, y, and b are all real numbers. Everything you're working with is just a real number. And by the way, b is greater than 0. Okay, so this thing is a positive. Now also, don't have b be a 1. Okay, that's very important. So pick some number for b. Maybe it's 2, maybe it's 5, maybe it's 10 or 17. Maybe it's a decimal like 0.5, maybe it's 2.758, maybe it's pi, maybe it's whatever, maybe it's e for all cases. It could be any real number. If you have a number to the x power equaling a number to the y power, what does that say about their exponents? Well, it says that they're equal to each other. And that should make sense. If I have 5 to the second power equaling 5 to the x power, well, obviously, they're the same thing. 5 to what power gets me 5 to the second power? This is the exact same form. It's 2. It's got to be 2. So we can use that idea to resolve. I think this was actually the first problem that we had in the practice problem. Let's take a look here. Notice that the base is a 4. Could I rewrite 64 to be 4 to some power? Well, if you know your exponents of 3, then yeah, you can. We could rewrite this as 4 to the 2x minus 1 power equaling 4 to the third power. 4 to the third power is 64. Well, here I'm saying 4 to some power gets me 4 to the third. Well, that means that these better, in fact, equal each other. 2x minus 1 better be 3. Whatever this number is right here, it better get me 3. So if I solve for it, we get 2x equals 4, x equals 2. And there we go. It works. Now, again, like the logarithmic problem, I'm going to say you can use this technique. However, it's not always going to be the most ideal. It worked very well for this problem. It was fantastic because this is a multiple of 4, right? This is a power of 4, actually. 4 is a root of it. Would it work for a problem like this or this? Not really, okay? Because I can't write 16 as a power of 8. And I can't write 8 as a power of 3 or vice versa. So it would be a little too difficult to do for any of these problems, other than in the very special case that your bases can in fact be represented like this. How often does that happen? Not very often, okay? In most cases, you're really going to have to use the standard technique that we've been going over, where you take the logarithm of both sides, okay? Now, if you can use this method, go ahead and use it. It makes your work a lot quicker and a lot easier. But Don't rely on it every time, okay? Now that's all I had to talk about for this video. What I'd like you to do is go ahead, give this some practice, practice both logarithmic and exponential equations, see if they're making sense to you, get a system down for yourself, and let me know if you have any questions. Let me know where you're struggling, where you need help in, or if you need me to go over anything more, or if you just have any comments, let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know what you thought of the video or any questions that you have, and until next time, take care.